In the last lecture, we studied about the superposition principle of forces acting on charges. This time, we are going to study about the electric field and its properties. First of all, I'd like you to understand what is an electric field. Consider that this is some point in space. Let's call it P. At this point P, if you're going to put some charge Q, okay, if you're going to put some charge Q, and let's assume that there is nothing else. Let's assume that there is nothing else anywhere close, so it doesn't have to interact with anything. Obviously, no force will act on this charge Q, right? Okay, but now consider a situation where before we put a point charge Q at that point P, before we put a charge over there, let's say that we put a point charge capital Q at this point. Okay, so let's say we have put a charge capital Q at this point, and now we put the charge small q at this point. Okay, so now we have got a charge capital Q over here, we've got a charge small q over here, right? So what do you think will happen to this charge Q? Okay, the small q. I'm sure you answer that it will experience a force, right? Now who has applied a force on that charge? Well, the answer is capital Q has applied the force on that small, on the charge at P, right, over here. So what this means is this charge Q, capital Q, somehow it's creating an effect, it's changing something about the region around itself, right? It's changing something about all these points, right? So that if I put, well, there's nothing over here, if I put a charge small q over here, right, the properties of this point, it has already been changed by this capital Q. So because of that change, this charge Q now experiences a force in some direction, right? Again, let me repeat what I've said, is that we have got a charge capital Q over here. This charge capital Q is somehow changing the properties of all these points in space around the charge capital Q, okay? So that now the properties have been changed such that if I put a charge small q over there at P, it experiences a force, right? It experiences a force, right? So you might say, well, there is Coulombian force between the two, right? So the question is, if there's only one charge and you put the second one, how is it that this charge can sense the presence of the other charge and start applying force on it, right? Or what is here, what is in this region, what's so strange in this region that if you put a charge over there, it gets a force, right? So obviously what is happening is that the charge capital Q is creating an effect in space. The charge capital Q is creating some sort of effect in space, and this effect is what is electric field. Okay, this effect is the electric field created by the charge capital Q. So what this means is that because of the presence of this charge Q, properties of the points in space around it, around this charge, they have changed, right? So earlier, without this charge capital Q, this point P was behaving so nicely. If you put a charge over there, nothing happens to the charge. Okay, right? But now magically, no magic here of course, so to speak of, what is happening is if you put a charge capital Q over here, it changes the behavior, it changes the properties of all these points. And now when you put a small q over there, it suddenly starts experiencing a force, right? So something has changed. There's some effect of this charge, and that effect is the electric field. Okay, right? So this is a very basic idea or very basic thinking or concept of the electric field, right? Now, electric field, well, in physics it's a quantity, and I'm sure you remember that quantities are something that can be measured, right? Quantities are measured. So how do we measure this effect, right? So that's what this topic is mostly about. How do we measure that effect, right? Okay, so first of all, we are going to define that effect, right? We will define the effect. I'm writing electric field and intensity in bracket because many good books around the world use the phrase electric field intensity, but your textbook, this NCERT textbook, uses the phrase electric field. Okay, both are correct obviously. So what is electric field or electric field intensity? It is the force acting on a unit positive test charge placed at a point in space, right? Okay, so electric field intensity means force that acts on a unit positive test charge placed at some point in space, right? So this definition sounds quite technical. Let's see the details. So consider that you have some positive charge Q. Okay, I'm assuming this is positive for keeping everything very simple at the moment. You have this charge capital Q. Like I said earlier, it's going to create an effect in space, right? And now let's say I want to answer a basic question like, I'm going to find out what is effect of capital Q at this point P. Okay, I have a question and I want to answer that. What is the effect of the charge capital Q at this point P, right? So how are you going to measure that effect? Well, let's try to answer that question. I'm going to explain it by using a very simple analogy. Think about wind speed and wind direction. Let's say somewhere, let's say on the terrace of your house, we want to measure what is the direction and speed of wind. How do you think we should do that? How can we measure the direction and the speed of the wind blowing over the top of your house? Well, you might say, so we'll take a piece of paper, we'll try to drop it, and when you leave it from your hand, the wind is going to carry it. The faster the wind, the farther it's going to get carried, correct? It will also show you the direction. So just like this experiment, if you want to find out the direction and the speed of the wind, you have to put something at that point, and you will notice what is the effect on that point, on that object, like the piece of paper. Same idea here. What we are going to do is to find out what's the effect of this charge Q at this point. To find out what's the effect of capital Q at this point, we are going to place a charge Q, small q over there, okay, at this point P. I've just drawn the same diagram again. So what we have is that this is the charge capital Q, which creates the field. So I'm going to call it source charge. In fact, why source charge? Because the effect is actually created by this charge, and we want to measure that effect, right? And this charge small q, which is placed over here, it's placed by us to test what's the effect, to check, to measure the effect. So that's why we call this charge q as test charge. Okay, now obviously the effect of a charge is the force that it could apply, but the idea is that if you are going to put a very small charge over here, the force on that charge will be very small, because of the fact that the force acting between two charges is given by this formula, the Coulomb's law, correct? So if this charge is very small, the force on it is going to be small. But again, suppose this charge was big, the test charge is big, so you take a big object, big charge, to test the effect, right? Then, according to this Coulomb's law, the force on it is going to be larger, then the effect of the charge capital Q will appear to be larger. I'll repeat what I said. If you put a small test charge, very small q, then the effect might appear smaller. But if you put a larger test charge q, then as this formula says, the force is going to be more. So it will appear that this charge has more effect over there. So how do we normalize this? It's a problem. If you put something very small, the effect of this appears to be extremely small. If you put small q is very big, then big charge, then the effect appears to be big. So what do we do about this? So we define it in a way that the magnitude of this charge q, small q, the magnitude of the test charge does not affect what we are trying to measure, right? Okay, so what we do is we define the electric field or electric field intensity in this manner, the force that is acting on the test charge, but that should be a unit positive test charge, right? So what we have is a unit positive test charge kept over there at this point P, right? So in any case you want to measure the electric field, you'd have to put a standard charge, standard test charge to test or to measure the field, electric field. What I'm saying is, it's not like you could put 2 Coulomb over here, right, to find out the effect of this charge q over there, and then when you want to find out what's the electric field at this point x, at that time you put 3 Coulomb. No, that would be invalid, because you have put different test charges, right? So what we should do is we should put the same test charge everywhere, and it has been taken to be the unit positive test charge. So wherever you want to measure the electric field, maybe over here or here, anywhere, what you have to do is you have to put a unit positive test charge at any of these points, right? So that's the basic procedure, right? Obviously this is a thought experiment. You can't hold a charge and put it anywhere, right? But we have defined it, and this is how we think we could measure it. So it's a thought experiment, right? Okay, so again, getting back to the calculations now. So what we have is, this is a source charge that is going to create the effect. We are set out, we want to measure the effect of this source charge. I hope you understand the word source, because it's creating that field. And to do that, here we are putting a charge which is our test charge, which we are using to test the effect of this charge, right? We're using this test charge to test or to verify or to measure the effect of this charge. Okay, now once we have got the forces, if we convert this definition to equation, okay, if I'm going to use mathematics to write an expression for corresponding to this definition, so let's see how it will work. So first of all, force on test charge. So the force on test charge, I should write it as FQ vector, is going to be K Q Q R squared. This is the magnitude again. So let's say that distance between these 2 points, or distance between these 2 points again, is R, right? Is it okay? Right? So FQ vector is K capital Q small q by R squared. There's only the magnitude, and now the direction, right? So for simplicity, let's assume that both of these are positive. Well, obviously that one is positive, it's a unit positive test charge. So for simplicity, let's assume that this is positive as well. Okay, so what we have is that the force on Q will be in this direction, right? Because if this is positive, that charge is also positive, they are going to repel. So this charge is going to push that charge out to the right hand side. So if I want to write the direction, well, I could write I caret, right hand side, but I'm not going to do that. I'm going to say that this is the radial direction. So I'm using a unit vector r hat. I'm saying it's a radial direction. Again, r hat is unit vector in radial direction. Now, radial direction means going away from source charge. Okay, so it's in the direction that is going away from the source charge, right? Clear? So what you could see is that magnitude is kqqq by r square, right? Because the distances are, and because we have assumed that this is positive right now, it's going to be in that direction. What if it was negative? Think about it. Suppose the charge capital Q was negative. Automatically, this expression takes care of that. You don't need to change it, because if capital Q is negative, okay, you are getting a minus sign, alright, and minus r hat, negative r hat would automatically mean, well, r hat is going away from the source charge, so minus r hat would mean towards the source charge, right? Okay, so you may have understood it, you may have not. We'll come back to that after a while again, right? So let's go on further. It's that FQ vector is K capital Q small q by r square r hat, where r hat is the radial direction going away from the source charge, right? As you can see it in that diagram. Again, to remind you, I've assumed right now that this is positive, but this expression works even if the charge capital Q is negative. this is the force on the tester. Let's read the definition again. It's the force acting on a unit positive test charge. What does that mean? What does that mean? It means I have to take Q's value as 1 unit positive test charge. But there is another simple way to do it. You could say that the electric field intensity at P is E vector, that's the symbol of electric field intensity or electric field, is equal to FQ vector divided by Q. Why so? Again, read this, it tells you the same thing. This is force acting per a unit positive test charge, right? Okay, so this is force acting on the charge, on the test charge, per unit positive test charge. What we are basically doing is, if we divide this force by Q, we are going to cancel the term Q in the calculations, as you can see over here. So what this means is, effectively we have put Q is 1, right? See, if you put Q is equal to 1 over here, you still get the same thing, right? So what this means is that you can also say that the electric field intensity at T in space is the force acting on the test charge divided by the magnitude of the test charge, that is FQ vector by Q. Okay, so what we have derived is finally that the electric field E vector is KQ by R square R hat, right? So this is the electric field, this is the electric field created by the charge capital Q at a point P in that diagram, at a point P, which is located or situated at a distance R, and this is the direction. Again, this is the direction R hat, going from left to right, is the direction or the position of that point P from Q. Okay, so this is what we have, right? Let me just write this whole thing again, summarize it for you. Okay, okay, so this is the gist of this whole topic for you. And the electric field intensity due to a point charge Q at a distance R from it, right? So the diagram obviously is in front of you, but for sake of completion, so here we have a point P and this distance is R, and this direction is R hat direction. Okay, so in that case what you have is this formula: E vector is KQ by R square R hat. So again, to remind you, this shows you the effect of the charge capital Q at this point. Okay, so if Q is larger in magnitude, obviously you are going to get a bigger value, a stronger electric field, right? Okay, if distance is more, let's say if you double the distance, because you're at double the distance now, the electric field intensity will become 1/4, right? That's what this is telling you, proportional to 1 by r square, right? Okay. Also, like I said earlier, this formula takes care of capital Q being positive or negative, right? Capital Q either could be positive or could be negative. That doesn't really matter, because if Q would be negative, in this expression you're going to get a minus sign automatically because Q is negative, and that takes care of the fact that electric field will reverse the direction, because the force on this charge, which is positive, will not be towards the right side but towards the left side. Okay, so that's really all about the electric field created due to a point charge Q. Okay, now we're going to talk about few properties of the electric field, right? Like its units and all that. Okay, so first of all, we're going to start with the unit, okay, which is actually very simple to understand. Right, some points about the electric field. So first of all, units, like I said. So what are its units? Well, it's very easy to understand what the units are if you have a look at its definition. It is the force acting per unit positive charge, right? You know, in simpler words, it's just the force acting per unit positive charge. So if I use this idea, I can easily write that the units of the electric field is Newton per Coulomb, right? There's also one more unit that you're going to study later, which is volt per meter, but you'll know about that in the second chapter, right? At the moment, I'm sure you can understand how we get Newton per Coulomb based on the definition. Okay, so that's for the units. Now, second is obviously dimensions. I want you to figure this out yourselves, okay, which is not very tough to do now, right? Third thing is that the electric field intensity, this is just to remind you again, the electric field intensity is a vector, right? That is, it has a direction. Okay. Fourth, the electric field intensity is a property of space, or you could say of point in space. What this means is that if I take this point P over here, at this point the electric field intensity is, let's say, 1 Newton per Coulomb. Now if I make the distance half, so if you go by this formula, let's say, you're going to get electric field intensity of 4, because if R is half, you can clearly see over here that electric field is proportional to 1 by r square, right? So what we have is, if you make the distance half, the electric field intensity's magnitude is going to be 4 times, right? So electric field intensity is a property of point in space. So at every point, over here, over here, over here, you may have a different electric field intensity, right? Just like I said about wind directions and magnitude, or I mean the speed, could be different at different places, right? Okay, so don't forget that it's a property of the point. The next thing is that the electric field intensity Again, it's okay if you do not write intensity. Like I've said, the NCERT textbook doesn't even mention that. So electric field electric field does not depend on test charge. What does this mean? So what I'm saying is that if you are to measure this electric field intensity by putting some test charge Q over there, it doesn't matter really what is the value of Q. I mean, Q could be 2 coulomb, right? But as long as you use the same test charge for every point, it's okay. Because of the fact that ultimately you are going to say that the electric field intensity is the force acting on that charge Q divided by the charge Q, right? So it's like if you have got a 2 coulomb charge, this F will be doubled compared to 1 coulomb, but this is also doubled because Q is now 2 coulomb. Understood what I said? Compared to a unit positive test charge, if you double Q, the force on that charge Q is also going to be doubled, because the Coulomb's law says that the force is proportional in magnitude to the product of the charges, right? So that's why both of these are going to get doubled and the end result is the same, right? So that means that the electric field intensity does not depend on what that test charge is, right? Okay, but yes, obviously we have defined it for unit positive test charge. Don't forget that. The definition should not be altered. It should not be changed, right? Okay. The next thing is, so you can see, like I said, it does not depend on test charge, but the electric field intensity depends on source charge or charges. Sometimes there may be multiple charges which are creating the effect of electric field. Okay, so the electric field intensity depends on the source charges and their distribution, that is how they are arranged or arrangement, right? We will we will cover this point in better detail sometime later, okay? But I hope you have understood that it depends on what is the source charge, right? As you can see that if this source charge was, let's say, 10 times higher, 10 times larger in magnitude, then automatically that would make the electric field intensity at this point P 10 times, right? So the electric field intensity doesn't depend on test charge, right? You can put whatever you want over here to measure, right? But it would depend on what's creating it. Well, that's pretty natural, okay, right? It's pretty natural because think about it this way. Let's say you have got some wind blowing, right? The speed of the wind doesn't really depend on what object you're dropping to measure that speed. Does it depend on that? If you drop a smaller piece of paper, or if you drop a slightly larger piece of paper, do you think the wind speed is going to depend? No, obviously not. Your measurement may be more or less accurate. Okay, that's a different story. But the effect that the wind has really at that point, that doesn't change. So same thing here. The test charge could be anything. That doesn't alter, doesn't change what this charge is creating in this space. But if obviously you change this charge, the source charge, if you change the source, the effect obviously gets changed. Okay, so we have these points over here, right? Now there's one more thing that I want you to note, which is not a property of electric field, not a property of electric field, but it's about test charge. Okay, so it says that to avoid effect, or rather to avoid force acting on source charge due to test charge. Okay, you might be wondering, what am I writing over here? I'm saying that suppose you have got a source charge Q over here whose effect you want to measure at this point P. You put a test charge over here. Alright. I said earlier that we should put a unit positive test charge. Right? That's what the definition says. Now, while that theoretically that's okay, but think about it carefully. If you put some 1 coulomb charge, let's say we are taking unit in SI, okay, SI systems. So 1 coulomb is actually a pretty big charge. So what will happen is that agreed capital Q will apply force on small q. We will measure that force, and you might say, okay, we have found out the electric field intensity. But there is also a side effect that's going to happen. Because capital Q pushes small q action, and you know, revenge must be taken, okay, revenge must be undertaken. So what we have is this charge, capital Q, is going to experience a force in the opposite direction due to small q. Now, how much force this experiences, that again clearly depends on the magnitudes of these two charges, right? But interestingly, the electric field, I'm just doing the scalar calculation, the electric field does not depend on small q like I've mentioned over here. So what's your best bet? What's the simple, what's the easiest way, convenient way to do this? It's that we keep test charge as small as possible. So, theoretically, this is how you could write it. And our math students will easily understand what this is. Even earlier in the chapter kinematics, we have studied about limits a bit. So what I'm writing over here is we should have the test charge to be as small as possible, that is q tending to 0, infinite symbol, very, very, very small, right? And in that case, the force that acts on this charge q will be negligible, because q is negligible. But yet, because we are going to divide by q again, we are going to get the same value of the electric field intensity, right? So please keep this thing in mind, and although the definition says the electric field intensity is the force acting on a unit positive test charge, right? But if you want to measure it without disturbing this charge, the way to do it would be to keep the test charge as small as possible, that is small q tending to 0, and in that case the force will be very small, right? So that's how you're going to save trouble, because if this force is more, the charge q, capital Q, is going to move or may move because of the force acting between them, right? So keep that in mind as well, right? So what we have discussed so far is what electric field is and some of its properties, right? As we finish this topic, I want to tell you about the last thing related to the point number 6. It is that the electric field intensity, because it depends on source charge, you cannot use this same formula for everything. Okay, so what I want all of you to understand, and it's more like a warning, okay, it is do not use E vector equal to KQ by R square R hat for all kinds of charge distributions. What do I mean? Later on, we are going to study about electric fields created by sheets and spheres and wires and all that. At that time, I've noted that many students are tempted to always use the formula E vector equals to KQ by R square R hat, irrespective of whether the charge is on a sphere or on a sheet or on a wire, right? So don't forget that this formula works only for a point charge. Don't forget that. Okay, so whenever someone asks you what is the formula of electric field, don't say E vector equal to KQ by R square R hat. No, that does not work every time. So you should ask a counter question. So electric field created by what source charge? Is it by a point charge? Then use this formula KQ by R square R hat. If it's by some other shape, do not use this formula. Okay, so this is not general formula. It works only for a point charge. All right. Okay. Now we're going to draw the diagram of electric field. You might say, how can we draw a physical quantity? Well, what we're going to draw is like what you see in a farm field, in a field or a farm. What you see is crops everywhere, right? Plantations, plants. So they are all maybe of different heights and aligned in different directions and all that. So similarly over here, so we're going to draw a diagram of electric field. Let's say that there is a positive point charge over here. I want to know about the magnitude and direction of electric field intensity at these 4 points. Let's start with the one overhead, this one. So you might say that if you want to find the direction of electric field at that point because of this source charge, you have to put a unit positive charge over here, Q, right? Test charge. That, like I said earlier, test charge could be anything, it doesn't really matter. It has to be positive, that's it. Okay, and you see what's the effect on that charge. That's positive, this is positive, both of them are going to repel. So what's going to happen is, this is the direction of FQ. But like we have seen earlier, the direction of FQ and E vector has to be same. Like, think of the basic formula. Force acting on the test charge per unit test charge. So if Q is positive, the direction is same. So what we have is that this is also the direction of electric field at this point. So instead of direction of FQ vector, I'm showing this as direction of electric field. Think of this point. Again, we put a unit positive test charge over here. It will experience a force in this direction. that means the electric field over there is also in the same direction, that is towards the right side. Just like that, over here you're going to see that it's in the downward direction. At this point it's going to be towards the left side. Okay. Now think of electric field direction over here. Put a unit positive test charge, see what direction it experiences force, and that's towards the right side. But then what's the difference between point 1 and point 2? Think about it. That's right, point 1 is closer to the source charge compared to the point 2, right? So because this is closer, what, you know, if I want to be very pedantic about it, if I want to be perfect about it, I have to draw a larger arrow for the point 1, because there the electric field is stronger, it has more magnitude, and I hope you remember that length of the arrow indicates the magnitude of the vector. So just like that, if I want to do it for this point, again it's going to be over there but longer, because the magnitude is more close to this point. So what I could do is similarly for all of these, but that's not it. Wouldn't the charge have an electric field at this point? Yes, obviously it has an electric field at every point around it. So over here it's going to be like this, and then a smaller arrow. Again, as you go away, the arrows are going to get smaller and smaller. So pretty much the same in all directions, right? But you see, that's not it. It's also in 3D. So it's going to come out over here towards you as well, right? And it's also going behind the board, okay, inside the board. So it's in 3D, don't forget that. So this is what the electric field diagram of a positive charge looks like. Now, just like that, if you want to draw electric field diagram of a negative charge, so let's say here's the source charge, which is a point charge, it's negative, and I want to know the effect of the effect of this charge, negative charge, at these points. So how do we measure that effect? Like I said earlier, take a unit positive point charge and put it over here. Okay, done. Unit positive point charge. See, this charge is unit positive. So the force experienced by this charge is in this direction, right? So going by the definition, the force acting on a unit positive point charge at some point in space, that is called the electric field intensity. So over here you have the electric field intensity towards the left side, because this source charge is going to attract this unit positive test charge. Now, just like that, if you talk about putting the unit positive point charge over there instead of this point, it's going to be attracted. Again, don't forget, this is unit positive point charge, so it's get attracted. Same thing here and same thing here. So what we have is that from all directions, the effect of this negative source charge is to bring the unit positive test charge closer towards the center, right? Just like that, if I'm going to put the unit positive test charge at a closer point, maybe over here, again over here, again over here. So compare the points 1 and 2. Compared to 2, 1 is closer, so the magnitude will be more, so I have to draw a longer arrow. Same thing over here, same thing over here. So, you know, by the same procedure, I could just draw a diagram similar to what we have over here. Okay, now what we are going to do is, because we are done with drawing the diagrams, we are going to solve a couple of numericals, basic numericals about the electric field. Okay. Okay, so here's the point P, and let's say here's the point A, right? And this charge is Q is equal to 3 coulomb. This distance is 2 meters, while this distance is, let's say, 4 meters. Okay, we want to find out the electric field intensity at these 2 points created by this source charge. So let's start. So first of all, at P. Okay, electric field at P. Don't forget the electric field is a property of that point in that space, right? So electric field at P can be given by, obviously what I could do is I could put a test charge over there, find the force that it will act on it, and then divide that force by charge Q again, and I'll get what I want. But now we're going to use the formula. Okay, so I'm using symbols, capital Q for the charge, RP for this distance, which is obviously going to be 2 meters, and RP hat means the radial direction from the source charge towards the point P, right? So let's say if we go by the standard XYZ convention of axes, so then finally this is going to be 9 into 10 raised to 9 multiplied by 3 coulomb divided by 4. And now the direction, it's towards the positive x-axis. So that's why I should write I hat. Again, RP means radial vector, radial unit vector towards P, right? So radial towards P means like going from the center towards the point P, so from here to here, right? So finally this is going to be 27 by 4, so that is 6.75 into 10 raised to 9 Newton per coulomb. Don't forget the unit. Okay, so this is the electric field intensity at the point P. Now if you want to do it at the point A, so electric field intensity at the point A, same formula again. So this is K Q 3 coulomb divided by RP square, RQ square, that is the distance between Q and A, right? So excuse me, it's actually RA square, so that distance squared is 4 square 16, right? Because this is RA, that's RP. Okay, so this is 16 and multiplied by the direction that we have to indicate, that is RA hat. So that's radial from Q to A. So I should be writing minus j hat. Again, be careful of the direction because this is supposed to be radial towards A. Okay, radial towards A. So that's why we have 9 into 10 raised to 9, that's k, q by distance squared, and direction is minus j hat. Okay, so finally, if I just do that calculation for you, it's going to be EA vector is minus and j hat Newton per Coulomb. Okay, that's what we already know. It's going to be 1 point, divide it very quickly, 6 and nearly 1.69 into 10 raised to 9. Okay, so this is going to be the electric field intensity at A point, right? So finally, again, minus j hat is indicating the direction, right? So think about how all of this would change if instead of 3 Coulomb over here, you might have some charge like minus 2 Coulomb. So obviously, because q is negative, this direction will get reversed. So you'll get minus I caret over there, and just like that here, you'd get plus j caret. So remember, as a shortcut, you could remember that electric field of a positive charge, okay, or rather a positive point charge is radial outwards. Keep a diagram like this in mind, that will help. Okay, but the electric field of a negative point charge is radial inwards. Both of them are radial, that is along the radius. Okay, so this is what we have, right? So remember these. Obviously, I've drawn something called electric field lines over here, but I'm sure you can relate it very easily with the diagram that I've drawn. Okay, so that's what we have for this topic, and next time we're going to study about superposition of electric field, just like there was superposition of forces, right? The next time we will study about superposition of electric field, which is more or less the same as for the forces, right? And we are going to solve a few numericals as well the next time. Alright, so goodbye till then.